In this and the following two lectures, we're going to be discussing some very basic ideas that we need to cover. I often like to call this, I guess somewhat illogically, things we have to talk about before we can talk about anything. If you started viewing these videos a few weeks after actually starting a chemistry course, then much of this is going to be a review. If you are entirely new to chemistry, then be sure to pay close attention to what's being covered here. It's fairly basic stuff, but without this background, it can be difficult to clearly communicate later information. We're going to be talking about things like elements, atoms, molecules, ions, ionic compounds, the periodic table, protons, neutrons, electrons, basic atomic structure, atomic numbers, and atomic weights. Let's begin by taking a look at something that appears in every high school chemistry book in the world. Okay, I admit I haven't looked at all of them, but I have never seen one that didn't have this. I'm referring to what is called the periodic table. Out of curiosity, I did an internet search using the phrase periodic table. I got 4,960,000 hits. So finding a periodic table to look at isn't exactly what you call a difficult task. There are many absolutely wonderful periodic table websites where you can learn more about any element than you probably would ever care to even know just by clicking on its symbol. I have always loved the periodic table. I loved it even before I had any real idea what it actually was. I just thought it looked kind of neat. But what is it anyway? Where did it come from? What does it tell us? And perhaps more importantly, how can we use the periodic table to make our study of chemistry a bit easier? There are actually several different ways of preparing a periodic table. I mean, it seems as if someone is always trying to come up with a more creative version. But by far, the most commonly used version is one that looks like this. Okay, did you get all of that? Of course not. So let's examine this most marvelous of tools and what it is all about. We might call this marching down the road of the periodic table, and along the way, I think we'll take a few side trips so we can discuss some additional things that I think it would be good to cover before we proceed further. The periodic table is a table that displays all of the known elements, obviously arranged into some sort of a pattern. And a good first question to ask might be, what exactly is an element? Oddly enough, the concept of an element seems to be something easily understood by students. Although when you try to rigorously define what elements are, you often end up finding that it's not all that easy to do without having to offer up a lot of qualifying statements and explanations. The idea of elements actually goes back well over 2,000 years. Some Greek philosophers offered up the idea that all the different substances that we see around us are actually made of combinations of a very few fundamental things. One of the very first ideas was that there was only one element, water. This notion is attributed to a Greek philosopher called Thales. Now, what in the world might lead a person to make this kind of a suggestion? Well, of all the substances on Earth, water seemed to be in the greatest abundance. Furthermore, water is the only substance that exists on Earth in all three forms under normal conditions. It can be found in solid, liquid, and gaseous form. Of the millions of substances that exist, no other substance, to the best of my knowledge, can make that statement. And life is impossible without water. Thales envisioned Earth as a flat disk floating on an infinitely large ocean of water. Now, this may sound ridiculous to us, but a logical argument can be made for this position. In fact, just for the sake of argument, I am now going to prove to you that everything in the world obviously must be made of water. Are you ready? Listen carefully. I hope you will be convinced. There are clearly only two types of things: living things and non-living things. Let's look at non-living things first. Let's pretend that we are living about 2,500 years ago. We go and get the purest water that can possibly exist, water from a clear stream. Now, you and I know that really isn't pure water. It contains a lot of dissolved minerals, but 2,500 years ago, this would have been considered completely pure water. Now we heat the water to boiling, and we let it boil until it has all boiled away. What do you see at the bottom of the container that held the water? Solid, non-living material. Well, since there obviously was nothing in the container except water at the start, these non-living substances clearly had to be made from water. So we conclude that all non-living things are made of water. Now, today we understand that the material left after the water was boiled away was always there to begin with. It consists of dissolved minerals that were in the water all the time and were just left behind when the water boiled away. But couldn't this be taken as evidence that all non-living things were, in fact, made of water? But what about living things? Well, let's do this. We'll take a container, fill it with dirt, and use some sort of balance to balance its weight against something else. Then we'll plant a small tree or a bush or something. And then for the next few months or years, we'll add absolutely nothing to it except water. Nothing. And of course, after a time, we will have a plant that weighs a whole lot. But after we take it out, the soil still weighs the same as before we planted the tree or bush, at least as accurately as we can measure. So where did all the material for the tree come from? Obviously, the water. So all living things must also be made of water. Okay, today we understand that the tree or the bush was actually absorbing carbon dioxide from the air and undergoing photosynthesis and all of that. But if you had no knowledge of this, might you be convinced that perhaps, just possibly, everything in the world might actually be made from water? Ridiculous? Illogical? I don't think so, given the status of scientific knowledge 2,500 years ago. Well, this isn't a course in the history of science, so we won't pursue this thing any further. All we're trying to realize here is that the concept of everything in the world being made of only a relative handful of basic elements is an old idea. You may even know that this water notion was later expanded into 4 basic elements, often called earth, air, fire, and water. But we clearly don't think of earth, air, fire, and water when we think of elements, at least I hope not. We think of things like copper and sulfur and gold. Now, many of these elements have been known and used since ancient times as well. And over the centuries, there arose the idea that, again, there were relatively few substances from which all other substances were made. The interesting questions were, how many of these substances were there? 2, 5, 50, 1,000? And what were they? It was clear that a lot of substances were obviously not elements. They could be separated into 2 or more different things. Therefore, they must be compounds. But if you kept trying to break some material down into simpler substances but never succeeded, then maybe that substance actually was one of these basic elemental materials. But how do you know that you just haven't tried the right technique? Perhaps you could break this thing down if you tried something else. Well, you really don't. Declaring something to be an element was basically a negative proof. They kept trying to break something down to prove that it was a compound. If they never could succeed, then they suspected it was an element. The truth was that for many years, they just didn't have adequate techniques. So some very stable compounds were thought to be elements for quite a while. But eventually chemists developed experimental procedures that were sufficiently sophisticated that they had great confidence that when they declared something to be an element, it actually was. So that has become what is called an operational definition of an element, something that cannot be broken down into simpler substances by what are often referred to as, quote, ordinary physical or chemical techniques. I actually feel somewhat uncomfortable giving you a definition like this, since we really haven't discussed what exactly we mean by ordinary physical and chemical techniques. So one can question how much meaningful learning is occurring here. What we're talking about is doing things like filtering, heating, melting, boiling, and passing an electric current through the material, often after it has been melted. The problem is that to really discuss this thoroughly and to cover specific things that don't fit nicely into our definition would demand too much time devoted to something that isn't all that important. It's almost always possible to nitpick at definitions like this using some specific examples that don't quite fit. But I think the idea is clear enough for our purposes today. The one thing I would like to discuss a bit further is the concept of an operational definition. There are two basic kinds of definitions in chemistry, operational and conceptual. That's also true of many things outside of chemistry, but we're going to stick to just chemistry. An operational definition is what you might call a very practical definition. For example, if you understand the operational definition of an element and have the experimental capability of doing what you are asked to do, you could get an A on a laboratory determine if this is an element test. In this example, you just take the substance, do the ordinary physical and chemical technique thing, and you have your answer. You perform the operation that is described, and you see if the thing fits the definition. But there is another kind of definition of an element. It's not going to do you any good whatsoever on a laboratory test. I mean, you won't be able to tell an element from an elephant with this definition, yet in many ways it is really the definition that is best, because it helps us to understand what makes something an element as opposed to a compound. These kinds of definitions are called conceptual definitions. The name kind of tips us off as to what they do. They get right at the concept behind the thing we're trying to define. The conceptual definition of an element is quite simple and I think relatively unambiguous. An element is a substance made of only one kind of atom. This definition is certainly not going to be of any use in a laboratory situation. We can't see atoms, so we'll just have to flip coins and probably get an F on the which of these substances is an element quiz. But it very cleanly and nicely lets us really understand what makes some things like copper and sulfur and gold elements, while other things like water are not. And the idea of atoms also goes back about 2,500 years as well. But the original suggestion that everything was made of indivisible, unchanging particles was only a philosophical argument, not a scientific one based on experimental evidence. And since philosophical arguments can be abandoned in favor of different philosophical arguments, the idea of atoms was eventually pretty much abandoned until the early 1800s. And even then, it was not totally accepted, even by many scientists, for about another 100 years or so. Something that virtually all my students are shocked to hear. Students are almost always very surprised to hear this because most seem to have this view that once a good idea is proposed in science, it is immediately understood and accepted by almost everyone. Au contraire. Unlike the sanitized version of science, often presented in textbooks, real science doesn't always move forward in an uninterrupted march in the right direction. There are often wrong turns and missteps along the way. That's one of the interesting things you find out when you study some of the history behind scientific ideas. But science is self-correcting. That's its essence. That is perhaps its greatest strength. And the march towards a real understanding of elements and atoms took centuries, with a lot of wrong turns along the way. But by 1869, a scientist by the name of Dmitri Mendeleev was able to publish what is generally credited with being the first true periodic table. In some ways, it resembled today's periodic table, but in other ways, it was very different. The biggest difference was that there were only a little over 60 known elements at that time. At the time this lecture was prepared, there were 118. Although you won't be going down to your local chemical supply house to purchase the latter ones, as they are very unstable, almost certainly do not exist in nature, and in many cases only a few atoms have actually been made. And Mendeleev's table had several missing elements. They hadn't been discovered yet. And there was no direct way to know that they were missing because elements at that time did not have numbers like they do today. We'll talk about what these numbers are a bit later. Mendeleev's elements were just listed in order of relative weights, lightest to the heaviest, which doesn't let you know for sure if you're missing an undiscovered element. But he and several earlier scientists had observed that the properties of elements tended to repeat themselves at regular intervals. In other words, if an element, let's say, reacted violently when placed in water, some element that was perhaps 8 elements later did the same thing. And then perhaps another 8 elements later, it happened again. So Mendeleev arranged the elements into what are often called families of elements. Because like human families, they do tend to have similarities. That's the essence of all periodic tables, from the earliest to today's modern version. In fact, Mendeleev was so confident in what he was doing that in several instances where arranging the elements by order of weight resulted in some element ending up in a family where it didn't seem to belong. He then suggested that it be placed in the following family, declaring that there was a missing element that was yet to be discovered. He even predicted several of its properties so that it would be easier to find. For example, the elements gallium and germanium had not yet been discovered. The next known element after zinc in weight was arsenic. But if you put arsenic right after zinc, it would go into the family that contains the elements boron, aluminum, indium, and thallium. But arsenic doesn't resemble these elements. It resembles nitrogen, phosphorus, antimony, and bismuth. So Mendeleev boldly suggested that 2 elements that would go between zinc and arsenic had yet to be discovered. More amazingly, based on family resemblances and trends, he predicted several of the properties of these elements. His predictions, in my opinion, were incredible. For example, here are the predictions he made for germanium, which he called ecosilicon, since he thought it would go right below silicon in his table, compared to the actual values. Rather than my reading all of these, since we really don't care about the actual values, just stop the video and compare Mendeleev's predictions to the accepted values. I'm pretty impressed by that, and I hope that you are too. Now, I'm showing you this example for one major reason, to let you see that knowing something about the periodic table and the properties of different families is a very useful tool to help you remember a lot of chemical information that would be virtually impossible to remember if learned in isolation. Today, there are no missing elements. Every element from number 1 to number 118 is accounted for. And perhaps more importantly, we now know how the atoms of different elements are different from each other. We know that atoms are not the most fundamental particles. They are made of smaller particles, namely protons, neutrons, and electrons. Now, the discussion of atomic structure in high school usually stops there because that's the level that allows us to deal with what chemists deal with. So we will stop there. Even though protons and neutrons are now believed to be made of even smaller entities called quarks. But that's not a subject for a high school chemistry course. Protons, neutrons, and electrons are as far as we need to go. Of all the topics in all of chemistry, the story of how our modern picture of the atom came to be has always been the one that I most enjoy teaching and talking about. There is great science and great scientists behind almost every piece of information contained in a periodic table. Perhaps you'll want to pursue the story on your own. Our job today, however, is to be able to read and understand what a periodic table is telling us and to use it to make our study of chemistry more efficient. So we won't be explaining how all this information came to be, the great experiments, the brilliant thinking, and at times the great debates among scientists. That is a very long story indeed. But we will be striving to get as much out of our periodic table as we can. So let's begin our study. Each element on the periodic table is represented by a symbol. Many of these symbols consist of only one letter and correlate very nicely with the English name for the element. Examples are elements such as hydrogen H, oxygen O, carbon C, fluorine F, iodine I, sulfur S, and phosphorus P. But since there are only 26 letters in the English alphabet, but there's over 100 elements, it obviously was not possible to assign each element a unique one-letter symbol. So the symbols of most elements consist of two letters. And in the case of those most recently discovered and not yet officially named, perhaps three letters. For example, since hydrogen had already been given the symbol H, helium had to be given a different symbol, so He was used. Other simple examples of elements whose symbols consist of two letters include things like neon, Ne, chlorine, Cl, copper, Cu, calcium, Ca, chromium, Cr, aluminum, Al, and magnesium, Mg. Please note that when a symbol consists of two letters, the second letter has to be a lower case letter. Small is not enough. The symbol for helium is He. He just doesn't cut it. So these are all two-letter symbols, and they correlate nicely with their English name. But English is hardly the only language, and the names of some elements were derived from languages other than English, Latin being the most common. Therefore, the symbols of these elements do not bear any obvious connection to their English names. Examples of these include sodium, Na from the Latin word natrium, potassium, K, from the word kalium, iron, Fe, from ferrum, gold, Au, from aurum, tin, Sn, from stannum, silver, Ag, from argentum, lead, Pb, from plumbum. Plumbers are called plumbers because years ago pipes were often made of lead. Tungsten, W, from wolfram. I'm going to assume that you will take the time, or have already taken the time, to learn the symbols of some of the more common elements. Now let's take a look at an individual element and discuss two important numbers that are associated with every element on the periodic table. We'll use chlorine, although most elements would work just as well. You have undoubtedly noticed that each element is numbered, from hydrogen, which is element number 1, to whatever element comes last on the periodic table that you're using, typically a number somewhat in excess of 100. Chlorine happens to be element number 17. These numbers, quite logically, are called atomic numbers, but they really are a lot more than just numbers. They have a very significant meaning. They tell us something very important about whatever element we are talking about. In fact, they tell us two things about an atom of that element. First, the atomic number of an element tells us how many protons are contained in the nucleus of an atom of that element. Nucleus? What's that? You haven't said anything about a nucleus. Yeah, well, I guess I haven't. Kind of making an assumption here that you already know that we believe all atoms contain an extremely small center called a nucleus. That these nuclei contain two kinds of particles, called protons and neutrons, and that the third kind of particle in an atom, the electrons, reside outside the nucleus in some fashion. I apologize if that's not the case, but I feel safe in making that assumption. So we might picture an atom looking something like this. Although, interestingly, it is actually difficult, basically almost impossible, to accurately represent an atom with a simple picture. That's a great frustration for many chemistry teachers, including myself. So right now, we're talking about the protons. We'll get to the neutrons later. A proton is one of the fundamental particles in all atoms. Protons are said to have a charge of, quote, +1. Now, you might ask the question, +1 what? What do you mean by a charge of +1? Go ahead and ask, I'm waiting. Thank you. I thought you'd never ask. That's a good question, with a somewhat subtle answer. What we mean by that is that electrical charge appears to come in discrete units, like integers, at least down to the level of protons and electrons. And the smallest unit of charge is the charge on one proton. The next smallest possible total charge would be twice that. No charge in between is possible. Charge comes in discrete units, as I said, sort of like marbles. I mean, you either have one marble or two or three or maybe 97, but you never have a fraction of a marble. Although I can always count on some smart aleck student talking about smashing marbles with a hammer. So we just arbitrarily call this one elementary charge and say that a proton carries one of these charges. Again, arbitrarily assign a positive value. This means that hydrogen, the simplest atom, has a nucleus that contains only one proton, while helium, the next element, has a nucleus containing two protons. Lithium would have 3 protons, etc., etc. And by the time we get to chlorine, element number 17, its nucleus contains a total of 17 protons. And that's true for all chlorine atoms. If you are a chlorine atom, my friend, your nucleus contains 17 protons, no exceptions ever. If you have 17 protons in your nucleus, you are an atom of chlorine whether you like it or not. But atoms are electrically neutral. So there must be 17 negative charges somewhere in a chlorine atom to balance the 17 positive charges. These negative charges, as you already know, are provided by the electrons. An electron carries a charge equal to that on a proton, but opposite in sign, in the sense that if you combine the charge on a proton and an electron, you end up with no charge at all. So we say that they are equal in magnitude, but opposite in sign. We say the charge on an electron is -1. So in all neutral atoms, which by the way is redundant, since atoms by definition have to be electrically neutral, the number of protons and electrons has to be equal, and both are equal to the atom's atomic number. So the atomic number of an atom tells us how many protons are inside its nucleus and how many electrons are outside its nucleus in a neutral atom. And notice that I said neutral atom, because it is possible to add or remove electrons from an atom, or a group of atoms, to form charged particles called ions. And that's what we'll talk about at the beginning of the next lecture.